Okay, so I'd like to review a little bit about complex numbers as we'd like to use these in um, something called a phasor notation, which shows up all across lots of realms of physics and electrical engineering. And, um, and so it's important that we just take a moment to kind of remember, why do we even use kind of complex numbers? Well, a lot of times we want to plot as sort of a position in a two-dimensional space. And so, for example, you might have a point here, which you could call as A comma B. That would mean that, for example, you have A going in this direction, some A, and you had B that was going up, right? So you have some B here, and if you've ever played Battleship, you take the battleship coordinates, and that tells you kind of which point you are here. So the deal with complex numbers is that we have a real axis and we have an imaginary axis. And we write a single number as A plus IB. And this is shorthand for meaning A going along the real part, real axis, and B going along the imaginary axis. And it gets us to this point, A comma B, in our plane. Where we're heading with this is that this A and B, they actually have a point that is in point in space that's being pointed to, and that point has some amplitude and it has some angle, or we call it as a phase. And a lot of times in the complex phasor notation, what we're actually imagining is that this arrow is going to be oscillating around in a circle. So in other words, if I were to take the projection, for example, onto the real axis of an arrow that was rotating around in time like this, I would see something that would be going, it would be large and then small, and then large in the negative direction, and then small again, and then large and then small. And that's a lot of times what, if you think about an AC or alternating current a system, then you could actually imagine that that this would be a great way to describe what's happening, is to say, well, I'm going to be talking about a circle, something rotating around in a circle, but I just want the projection kind of like onto one axis. So I want to show something that, in other words, like a voltage that is high and then low and then high and then low. So something like this. This might be our picture here, is that we have a voltage as a function of time. So this would be an example of the type of thing that we're trying to describe. Now, in circuits that are using in circuits that are using different kinds of components, such as resistors, capacitors, and inductors, we're actually going to want to take a closer look in and see if we can generalize the picture a little bit and make some sense of what's happening with regards to the current and the voltages. And we'll actually, where we're eventually heading here in this discussion is to talk about complex impedances and how we can use these to understand how the currents will be responding to oscillating voltages in a circuit. And then ultimately this discussion leads to the description of electromagnetic waves, which also use the complex phasor notation. But for now, we'll just focus on a system of AC circuits, and then we'll generalize from there. So before we get to the AC circuits, let's also talk about these complex numbers. So I wanted to introduce something called the Euler's theorem. And so what's interesting is that this complex number, we can just write it as z for right now. This z is some a plus ib. But actually, if you notice here, that a plus ib, a is, if let's say the amplitude of this thing is just 1, then this a is just the cosine of this angle, and the b is just the sine of this angle. So I could rewrite this z here as equals to the cosine of theta in the real direction plus sine of theta in the I direction. So in other words, this is my a plus ib, right? Is this thing here. And I'm going to do a cool little trick here to show you that we can actually cast this form into a more convenient form that's it's going to have some mathematical advantages. So actually, one thing that you might notice here is that what if I were to take the derivative of this z with respect to theta? So I'd say dz by d theta. Well, derivative of cosine, I'm going to look at cosine here. It looks like that the slope is 0, and then as I get down here, the slope is kind of negative. So it looks like this is giving me a minus sine of theta. Okay, what if I took the derivative of sine? Well, if I have that sine function, I'm kind of thinking about what it looks like here. It looks like it has a maximum slope, and then it levels off to 0. So that to me looks like a cosine. So I have plus I times the cosine of theta. So you can check those things. And actually, if you notice here, I'm just looking at this, what I just got, compared with what z is here. And it looks to me like if I were to multiply this thing by maybe a minus I guess. Let's see here. If I were to multiply this one by a minus I, then I would be very close to getting. Let's see here. What would happen if I did that? So if I took minus sine of theta and I multiplied by an I, and I multiplied this I cosine of theta by an I know that I times I is equal to minus 1. And that is because this I is equal to the square root of minus 1, right? It's kind of a weird thing, but that's the definition of it. So it must be that I squared is equal to minus 1. So there's my I squared. So if I take I times z, I'm going to get a minus I times the sine of theta, and then I'm going to get a minus the cosine of theta, because I squared, right? So actually, that to me looks very much like the original here, cosine plus I sine, but just with a minus sign. So that's equal to minus z. So in other words, it looks like this. Oh, I'm sorry. This was our dz by d theta here. So it looks like then if I multiplied this by a minus I, then this is equal to minus I times z. So that's interesting, actually. This looks like a separable first-order differential equation. So I can just say that this is dz over z, and this is equal to, looks like, oh, let's see here. I wonder if I made a little mistake here. So if I multiplied by an I here, I get a minus 1. And let's see here. Derivative of cosine is minus sine. Derivative of sine is cosine. Okay, that all looks okay. And what I want to say then is that, okay, let's try it the other way around here. If I multiplied this by an I, and I multiplied I times I, this would give me a minus 1. So actually, okay, I caught the sign error. This should be equals to a plus IZ. So it looks like this is equal to plus I times d theta. So, so we can basically then, at this point, you can say, well, it looks like if I took the integral of both sides, I would get the logarithm of z is equal to I times theta. Or in other words, that z is equal to e to the I theta. And it turns out that this generalizes here, is that I could rework exactly the same definition, but including this factor of capital A, which is just multiplying by all these things here. And I could get that, so this is for z that has just this situation here of cosine theta plus I times the sine of theta. And so if I were to then instead write, I could write a z as generally any a plus ib, which is equal to some a times e to the I theta. So I guess what I want to say here in summary is that I wanted to convince you that this is a weird fact here, that this is equal to cosine of theta plus I sine of theta. But I wanted to convince you of this idea that writing something in kind of a vector notation, right? So something in the real part and something in the imaginary direction, right, as a kind of a two-dimensional coordinate, could then be re-represented as something along a unit circle. Or if you want to stretch that unit circle, put an A in front of it, and you can actually then scale this A here. So, so this is kind of exciting. This is like a different way of writing our complex number in terms of an amplitude and some phase factor, instead of just keeping it as a simple complex number. So So this is kind of an interesting way of describing things. But what do we actually what can we kind of benefit from this, or how can we benefit from writing things in terms of amplitude and phase? Well, one way is that actually we can think about the notation of using using complex numbers to describe voltages. So, for example, if I had some V of t, some driving voltage in a circuit that was equal to some V naught times e to the I omega t. Well, this means that omega t, if you remember from some previous notation, that omega is going to determine the frequency at which something is going to be moving around in a circle. In other words, the cosine of 2 pi times t over some capital T. This means that every time that little t becomes capital T, we will have gone around by 2 pi. And so you can imagine that I could write my voltage like this, and that would be kind of a shorthand way of writing that it's V naught times the cosine of omega t, which is actually what we have written here. So if I wanted to figure out the amount of time between these here, I could say that this is that capital T. In other words, that the frequency is equal to 1 over t. And it looks like then that must mean that my omega is going to be equal to 2 pi over t, or 2 pi times f, according to this concept here of trying to make it line up so that every time that t gets to be some multiple of capital T, then I've gone through one complete oscillation. So, so this is cool because what we can do is we can actually rewrite this V. I'm going to write it as V complex here is equal to V naught times e to the I omega t. And at the end of the day, what I'm going to actually want to do is I might try to solve something, like solve for the current in a circuit or solve for some other voltage drop. And then what I'll end up doing is in the end of the day, I'll take the real part, and that'll actually give me the information that I'm looking for, which is how this voltage is actually behaving in my circuit. So okay, so let's try an example then. If I had let's say a driving voltage here, so an AC voltage, and it's going through a resistor here. So I have some V of t, and I have a resistor here, R. Let's say I wanted to figure out what is the current at any moment in time that's going through this thing. Well, it probably seems pretty trivial to you if you remember Ohm's law. Ohm's law says that the voltage drop across this resistor is equal to the current that's going through this resistor times its resistance. So let's write that in words. This says V of t across the resistor is equal to I of t times R. So in other words, we can just solve for I of t here. And if I use this as my voltage here, I can say that I of t squiggle is equal to V naught times e to the I omega t, looks like divided by R. Okay, cool. So if I actually wanted to figure out then the actual current at any moment in time, then I could just write that I of t actual is equal to the real part of I squiggle of t, which is equal to V naught over R times the real part of this, which is going to be the cosine of omega t. Great. So then, for example, if I put in, for example, that omega t is equal to pi over 3, for example, I'll get that the cosine of pi over 3 is 0.5. And so I can actually then start to see that, okay, then this would be V naught over 2R would be the current at some particular moment in time, for example. So I'll just write for example. And so you can actually then compute the current at any given moment in time that's going through this resistor by using this complex notation. Now, this might seem like a heavy gearworks for just calculating the current through a resistor, but in our next examples with capacitors and inductors, I think you'll see how we can actually find this to be a very useful mathematical approach. Now let's take a look at the voltage drop across the capacitor. We're going to start to see the power of using these complex numbers in just a moment here. So if I took a look at an AC kind of voltage across not a resistor, but rather across across a capacitor here. I might ask a similar question. What is the current that is going through this thing here? Clean this up just a little bit. And so what we could actually say here is that I know that the voltage drop across a capacitor has to do with how much charge is being stored on either side. So we might have a plus Q on one side and a minus Q on the other side. And the voltage drop across a capacitor is defined as the charge per capacitance. Or in other words, you could think of it as the other way around, that capacitance is defined as the amount of charge per volts, right? So in other words, if I were to apply a particular voltage across there, that would tell me that how much kind of charge difference I can build up across my capacitor plates. Of course, the capacitance is some geometrical factor, and it has something to do with maybe what kind of dielectric is inside and how big the plates are and so on. But nonetheless, my driving voltage is just going to, again, be my V naught times e to the I omega t here. So I could say, all right, well, why don't I just do this in a kind of a complex number notation, and at the end of the day, I'd like to try and figure out what my current is by solving, basically by taking the real part of whatever complex current I come up with here. So here's my VC, and I notice actually that I'd like to make a relationship between current and voltage. So actually, I'm going to take the derivative of both of these sides here. So I'm going to say that I'm going to have delta VC, and I'm going to take the derivative of this is equal to Q dot divided by C. And I'm going to call Q dot for right now to be equal to the current. And in some cases, we're going to have to be careful about whether Q dot is actually equal to current or is equal to minus the current. But for right now, I'm going to define Q dot as equal to the current, right? So this is the rate of charges passing by a given point. And so here, if I take this as being my V naught of t, if I took the derivative of this, in other words, if I did a d by dt of e to the I omega t, what would I get? Well, it looks like to me that I would be bringing down this I omega. So I would bring down an I omega, and then I'd have e to the I omega t. So in other words, the voltage drop dot looks like it has an I omega, and then times my original, which is V naught times e to the I omega t, which is just still delta VC. So in other words, just by taking a derivative of this complex exponential, right, so d by dt of V naught e to the I omega t, I'm claiming here is just bringing out an I omega, and I'm still left with V naught e to the I omega t, or, which is just V of t, right? Or so by V squiggle if you'd like. So in other words, taking a time derivative just pulls out an I omega. Here, I'm going to be left with I over C. So actually, I can solve for I at this point here. My current, my I squiggle, is going to be equal to I omega C times delta VC. Or if I'd like to cast it into kind of a V equals to IR kind of format here, I could say that delta V across the capacitor is equal to 1 over I omega C times I. And again, I can just put the squiggles here to remind myself we're dealing with complex numbers. But this is very interesting here. This is like V equals to I times R. So it's like I have an R that's equal to 1 over I omega C. Whereas in this case, if we did V is equal to IR, the R would just be R in the case for a resistor. So apparently, I could write then R for a capacitor, but that calling it that R already kind of sounds a little confusing because we've already used R for resistances. So we're going to introduce this new number called Z for the complex impedance, which is like an R. And that's going to be equal to 1 over I omega C for a capacitor. So this is very interesting. This is an idea here that the complex impedance for a capacitor is equal to 1 over I omega C, or minus I over omega c, because if you remember, if I just had a 1 over I, then I could multiply both top and bottom by I, for example, and I would end up with an I over minus 1, which is equal to minus I. So in other words, 1 over I is just equal to minus I, is kind of what I'm suggesting here. What about for an inductor? So that's a capacitor. Let me get another color here. Talk about our inductor. So for an inductor, I'm going to actually approach it from a little bit of a different perspective. I'm going to say that I have my inductor component, and instead of thinking first about the voltage as being the complex phasor, I'm actually going to go about it the other way, and I'm going to say that current is defined as some I naught times e to the I omega t. And I know that the voltage drop across an inductor is equal to its inductance. This is the inductance of this element here. Suppose I should have done the same thing over here for this capacitor here. And this is equal to L times di by dt. So again, what happens if I take the first derivative of this thing? To me, it looks like I'm going to pull down an I omega. So this looks like it's going to be L. So here I'll just do it out because it's nice for our learning here, is that if I do d by dt of I naught e to the I omega t, then the I naught is a constant, and I'm going to be taking the derivative of e to the I omega t, which is going to bring down an I omega. So I'll end up with an I naught times an I omega times e to the I omega t. And this here is just I. So in other words, d by dt is equal to I omega times I. Okay? So here I'm going to do delta V is equal to di by dt, and I can say that this is going to be equal to L times I omega times I. So again, we can actually we can see immediately, without any rearrangement, that V equals to IR is actually, this is my effective R. So I'm going to call this my ZL. In other words, that my impedance for inductors is equal to I omega L. So very cool. We actually now have some complex impedances. Now, what do these actually mean physically now? Well, let's go back to the case for the capacitor here. If I have this ZC and I wanted to figure out what the current is that's going through this capacitor as I'm varying the voltage, I can actually take a look directly and see that I can just figure out the current going through this capacitor here is equal to, let's see, it looks like it's going to be V of t over ZC, right? And it looks like this this ZC is simply 1 over I omega c. And so if I do 1 over that, I'll get I omega c times times V of t. Or here's another way I can look at it here, is that actually this is going to be I times omega c times V naught e to the I omega t. Okay, so actually in the case where we're trying to figure out the current here, we found that actually if we were driving with a cosine term, we found that the current was also cosine, meaning that the voltage and the current, that they're moving together. But actually, if I think about this here with this I, if I go back to my picture of having this complex plane here of 1 and I here, and thinking about the angle, right? So if I have some phasor here with some angle, if that angle is equal to 0, then my e to the I 0 should be equal to 1. But if this phase here is equal to pi over 2, then we should be over here and we should be completely along the imaginary axis. So if we have e to the I pi over 2, we should have I. So that's actually, that's interesting because then that means 90 degrees gives me this I. So this I here is actually 90 degrees. And I can fill in the rest if I'd like here. And I could say that e to the I pi is equal to minus 1. And down here, if we went around by 3 pi over 2, that's e to the I 3 pi over 2. Or that's also, if you want to go the other direction, e to the minus I pi over 2. that's all equal to minus I. So you can kind of see this sort of circle emerging here. And if I take it back to this, this concept here, this is actually equal to e to the I pi over 2. So here I can write this as omega c v naught times e to the I pi over 2 times e to the I omega t. That's very interesting because that's telling me then that the current, if we have this kind of prefactor here, if we have e to the I omega t plus pi over 2, that's actually telling me that my current that's going through the capacitor is always 90 degrees, or pi over 2, ahead of the driving current. So in other words, for a capacitor system, if I have a cosine voltage driving like this, then my current is going to look something like exactly the same, but shifted ahead by 90 degrees. So it'll already be here, and it'll already be, let's see, here, and it will already be here, and it'll already be here, like this. So what I'm trying to draw here is that if this is V of t here, then this is the I of t in my capacitor system. So this here is for the capacitor. And I can see that the current leads the voltage by 90 degrees. So this is really interesting. So you can see that wherever the voltage is, that the current is already sort of peaked just 1/4 of an of some, how do you say, 1/4 of the period of this thing before the voltage peaks. Now, is the same thing true for the inductor? Well, I'm running out of a little bit out of space here, but you can actually see pretty clearly that that I, in this case, if we do again like a V equals to IR kind of relationship, so here's my V is equal to I and then kind of R, but it's my complex impedance, I can say I is equal to V over Z, right? And again, I'll just get that this is a minus I over omega L. Of course, I was doing a 1 over I omega L, so I brought my minus I upstairs just for clarity. And then I can multiply this by my V. And again, I can just say, oh, minus I. Oh, if I just go back over here, minus I is the same thing as a e to the minus I pi over 2. So in other words, this is equal to 1 over omega L times V naught times e to the I omega t minus pi over 2. That's kind of cool. That actually is telling me that the current is lagging the voltage in an inductor case by 90 degrees. So again, if I can draw a picture here of the driving voltage here, so I'll try to stay consistent with my colors. So, whoops, I can say that I'm going to do my driving voltage like this for an inductor, and then I'll actually plot the current as lagging by 90 degrees. So I believe, let's see here, if I'm going to lag by 90 degrees, then as time goes forward, this thing is going to be, let's see here, this has gotten to the bottom, then this one has gotten to the bottom, okay? And this one's gotten to the top, and then this one has gotten to the top. So something like this. So here is my I of t, and here is my, oops, and then here is my V of t. And again, it's pretty straightforward at this point, is that yes, this is my complex current, but if I wanted to figure out my actual current, then I'm just going to take the real part of this I tilde, and I'm just going to get V naught over omega L times the cosine of omega t minus pi over 2. And we can play some games to cast that into a sine or a cosine term. In fact, I think we can just read it off directly here, that this looks like you could write the cosine of omega t minus pi over 2 is just simply being the sine of this thing here. So we can rewrite these equations as we'd like. And again, here you could write this plus pi over 2. In this case here, we could actually write that the actual current here, so I of t, is actually equal to omega c v naught times the, it looks like a minus sign in this case, but I'll just write it as a cosine. Oops, looks like we're running out of room over here, so I'm just going to write it below here, that this is omega cv naught times the cosine of omega t plus pi over 2. Cool, so we're getting somewhere. We're actually able to now write down these complex impedances, and after erasing a few things, I'm going to actually now summarize these complex impedances and how to use them to analyze the properties of a few different kinds of filtering systems. So let's see. In summary, we have the complex impedance of a resistor is just simply R, right? So that's kind of the most boring case. And then we derived that we had the complex impedance of a capacitor is 1 over I omega c, or is equal to minus I over omega c, as you like. And again, the complex impedance of an inductor element is equal to I omega L. So the wonderful thing that we can now do is that anytime we want to figure out to do a Kirchhoff's voltage loop through a circuit that contains a capacitive element or a resistive element here or an inductive element over here, is that we can actually just apply these complex impedances and use kind of a V equals IR as we'll demonstrate in the next clip. Okay, so just to review what we just figured out, we found that we can actually just write the impedances of different circuit elements, such as a resistor and a capacitor and an inductor. And so actually, if we think about each of these elements here, we can have a driving voltage that would be like a V naught times the cosine of omega t. And our understanding is that we're writing this in a complex phasor notation, meaning that in the complex plane, that we have kind of a vector that basically has an amplitude of V naught, and that this thing here has some phase omega t, and that as time goes forward, this thing is spinning around the complex plane. And then one thing that we're interested in is we'd like to know how different voltage drops or different currents are behaving or responding in this system. And one of the things that we found so far was that for a resistor, the current is in phase with the driving voltage. And then we found actually that for the current that the I was actually leading the voltage by 90 degrees. And then we found actually for the inductor part that I is lagging the voltage by 90 degrees. So kind of that gives us at least sort of kind of a summary on the outset here, is that if I simply had a voltage that was revolving around in time like this, then we could actually watch the current that's, say, going through a capacitor, and we could actually, or a current that's going through an inductor, and we could see that for the capacitive case, that we'd always be, this would be my vector that represents my current through a capacitor, for example, and we'd find that it was always 90 degrees ahead. So if I can sort of visually sort of display with my two markers here, as this voltage is rotating, this current across the capacitor is always 90 degrees ahead. So this is kind of our way of thinking about this here. And similarly, our current that's going through an inductor is always going to be 90 degrees behind. So meaning that as this is spinning around here, then we're always going to be phase lagged by 90 degrees. So that's kind of a good way for us to visually think about it. And whereas for a resistor, that the resistance is always going to be in phase. So my driving voltage and my current are always going to be in phase with each other. So this kind of summarizes each of these circuit elements, and hopefully I've given you some motivation for this idea that you can use this complex number. In other words, you can use the fact that that if you wanted to figure out a current, you would, for example, use I is equal to V over Z. And then whatever this Z is, we can actually figure out its phase. And so what I'd like to now do is maybe take a look at a couple of different circuits with different elements in there. So, okay, let's just pick an example here. So I'll have a driving voltage, and let's say that I have a resistor and an inductor, okay? Just kind of pick that a little bit randomly here. And if I wanted to do my V equals IR, I could go around this loop here. So I'm going to have a current going through this thing. Here's my R, here's my L, and here's my V that's driving this thing. So I'm going to have a V minus IR minus IZL equals to 0. So I just wrote down as if I just basically treated this thing as if it was a resistor, right? Even though I know it's an inductor, right? But I'm now saying that it's like a resistor that has this complex impedance. So then I can just basically solve for my I is equal to V squiggle divided by R plus ZL. It really is that simple. And so then I can write now that my, my I squiggle is then equal to V over R plus, and then I need to use the complex impedance for how do you say, for the inductor, so which is I omega L. Now we need to do a little bit of kind of, how do you say, rearranging here to figure out how do you get this into something that's going to be a little bit more obvious for us to kind of read off. And what I'll do is I know that I can actually multiply top and bottom by a complex number to get the complex number up on the top, because it's a little bit harder to sort of immediately look at that and say, yeah, I think that the current is going to have a phase shift either forward or backwards. I'm not really sure. So I'm gonna write R minus I omega L, R minus I omega L, and I'll be left then with V squiggle times R minus I omega L over R squared plus omega squared L squared. So this is cool. I'm actually getting somewhere. And I can see here that actually there is a, there's going to be a part that's in phase, and then there's going to be a part that has a minus I omega L. So then it looks like there's going to be a part that is, how do you say, minus I omega L. Well, I know minus I is this minus pi over 2, right? So here, minus I is equal to e to the minus I pi over 2. So there's actually sort of some component that is phase lagging and some part that's in phase. So in truth, it's not going to be exactly in phase, and it's not going to be exactly 90 degrees lagging. It's going to be somewhere in between. So what we can actually do is another way of going about this. So this is correct, and if we take the real part of this, then we'll get the current. But perhaps a more intuitive way of dealing with this is to think about what your effective Z is. So Z total here is simply equal to R plus I omega L. And so if I write that in the complex plane here, I have a Z which has an R going this way and an I omega L which is going up like this, right? So actually I can think of in the complex plane, I can think of my Z total as being a vector sum of these two components here, one that's going along the real part and one that's going along the imaginary axis. So now, could I possibly convert that into kind of an amplitude and phase? Well, it seems like the amplitude is just equal to the square root of R squared plus omega squared L squared. So I could write that as my amplitude. And then for my phase, could I write that as then, what is this angle here? Well, I know that the tangent of this angle is equal to this over this, right? So in other words, my theta should be equal to the arctangent of kind of this B over A, where this is some B and A here, which is in this case is just equal to the omega L part over R. So I can write this as the arctangent of omega L over R. So this is actually kind of helpful because this will tell me about what the actual, how do you say, phase either lead or lag is. And so I can actually kind of read off this angle here visually, right? So of course I know that taking an arctangent, we need to use maybe some calculator to actually compute this, but nonetheless, that's how we do it. But look, you can actually visually read this off, that if omega L is this much and R is this much, then this is your Z with this phase here. And if we're actually computing I is equal to V divided by Z total, well, actually, that gives you a phase shift up, and if we're doing 1 over that thing, right? So in other words, this is going to be my effective theta here, right? My theta is going to be this, and if I can see visually that it's this here, I can actually see the amount which I'm lagging by. So I can then write directly here, and I can kind of visualize this, that if my V were, for example, right here at this moment in time, so here's my V at this particular moment, then I can actually see that, that my current should have this same theta, but it should be lagging, right? So this is my current, and remember that it's, you might ask, well, is it the current going through the resistor or the current going through the inductor? And if you remember, actually, because of the charge conservation, that it should be the same, that any charge that's going into here should go out of here, and any charge that's going into here should go out of here. It's always the same amount of current in all of these circuit components because there's no other place for them to go. So, so this is really cool. You can actually immediately write down, oh yeah, the current here is lagging by this angle, and I can calculate that angle. So this is pretty cool. Anyway, you can also see here that if omega, if it was very, very low frequencies, then you'd basically be in phase because this part here would be shrunken down, and your Z would be very, very close to the real axis, which in this case means that this I would be following very, very close to V. So hopefully this is starting to give you an idea that this is actually a really nice tool. So whether you do it this way and end up taking the real part, or you take a Z total here, given that Z total is here, you'll end up getting exactly the same answer. So plugging in the result here, that I have 1 over the square root of R squared plus omega squared L squared, and then I have an e to the minus I theta, where theta is given by this arctangent. This is all 1 over Z total here, and I'm going to multiply by then V naught times e to the I omega t. So again, remember that phasors, that the exponentials that multiply, that means just that their phases are adding with each other. So in other words, we can calculate then the magnitude of the current and the phase. And so just taking this to its last step here, I'll say that this is V naught divided by the square root of R squared plus omega squared L squared times e to the I omega t minus theta, again, where theta is given as the arctangent of omega L over R. So that's nice. Like this is actually then the amplitude of my current, which I can compute here, and then I can actually see then how this thing is evolving in time with a driving voltage. So that's a great example of just how to follow the current in a system. Now, another thing that might be interesting that we might want to try out is we might want to see what the voltage drop is across any one of these elements here. And so in order to demonstrate that part, I think I'll work through an RC circuit in order for us to take a look at how we can think about the measuring the voltage drop across one of these components as providing us with a filtering aspect. All right, so as a further example of this, this analysis of circuits using complex phasors, I'm going to take a look at what is called as an RC filter or an RC circuit. And so the way that this is typically drawn here is that we'll have a driving voltage, and just like my RL circuit, or resistance and inductance, I'm going to have an R and a C in this case here. And ultimately what we're going to do is we're going to either measure the voltage drop across the resistor, or we're going to measure the voltage drop across the capacitor, and we're going to just see what the voltages look like. So again, we have a driving voltage of e to the I omega t times some V naught. And what we'd like to do is ultimately come up with a what is called a transfer function that tells me if I were to measure the voltage drop here and divide by the voltage drop over here, then like how much would I get? How much amplitude would I actually get of my signal? So to analyze this here, I'm going to again do my Kirchhoff's voltage loop, where I'm going to go around a complete loop around this circuit here, getting a voltage boost here, getting a voltage drop here across the resistor, and getting another voltage drop across the capacitor, where I'm going to be using this ZC. So I'm going to say just minus I times ZC equals to 0. So I'm just writing that down. And again, I can then solve for the current, which is equal to V tilde divided by, looks like R plus ZC. So in other words, following the notation from before, I can actually figure out, well, what is my total impedance at this point here? And I can say, well, I've got R going this way, and ZC, but that's equal to minus I over omega C. So actually, I'm going to find it a little bit more intuitive right now if I just write this as a minus I over omega C. So that means that here I'm going to be doing a minus I over omega C in this direction. So if I add these two vectors, then my total how do you say, total impedance, total complex impedance, points down, right? So that means that when I divide by this, I'm overall going to get a phase lead of my current. Okay, so we can actually then say that Z total should be equal to the square root of, well, here, let's fill in the blanks before I start, so I can make sure that I'm not skipping too much steps here. So I can say that Z total is equal to R minus I over omega C. Okay, and that's also equal to the square root of R squared plus 1 over omega C squared, so I'll do omega squared C squared here, times e to the I arctangent of, now here I'm going to have a minus 1 over omega C over R, so minus omega RC all down in the bottom. So that's my phase. So this is my complex phasor notation here, and so also one of the properties of arctan is I can bring this minus sign out if you'd like, but in any case we can see visually here that this angle should be negative, so that when we do 1 over that, then we should end up getting a positive angle, meaning that we should get a phase lead. So nonetheless, this can be written then as a V tilde over my complex impedance here. So we're going to do R squared plus 1 over omega squared C squared. And then this is going to all be times e to the minus I theta, where this is going to be my theta here. So, okay, cool. So now I can actually start asking questions like, hey, wonder what the voltage drop is across my resistor. Well, here, if I put some leads across this thing here, and I were to try to measure the voltage drop across the resistor here, then that would just be equal to the current that goes through this times R. So I can just write down directly that delta V times R is equal to I times R, which is equal to, looks like V tilde over, I'll write here as R squared plus 1 over omega squared C squared to the 1/2 times R, and then times e to the minus I theta. And I'm leaving the theta as defined like this just for sake of not having to write too much stuff right now. And so actually, one thing that's really cool here is that I said that we could define a transfer function, which is basically taking whatever my voltage drop is across the resistor divided by the driving voltage. So actually I could see then that my V out, let's say, measured across the resistor, divided by V in, which is my driving voltage, is just going to be equal to all this stuff divided by V tilde. So actually, and I'm going to take the absolute value because at the moment I don't want to worry about this phase term too much. I don't want to get too preoccupied by this. And what I can do then is I can say that this r here, I can kind of, how do you say, rewrite this as 1 over r. So for example, I can then write that as, let's say, 1 over r times r squared plus 1 over omega squared c squared to the 1/2. And then I can distribute this into the square root here, and I'll get actually 1 over, and this looks like to be, I'm going to have a 1 over r squared and then a 1 over r squared here. So when I distribute that, and it looks like I'll have 1 plus 1 over omega squared c squared r squared to the 1/2. So this looks like my transfer function here. So in other words, if I had really, really, really high frequencies here, then this term would be really, really small, and I'd get 1 over 1. Okay, let's say that omega was a small number, right? Well, if that's a small number, that's going to make this number very, very large, meaning this 1 doesn't matter, and we'll have 1 divided by a really, really large number. So that means that if I measured the voltage drop across the resistor, then I would have low frequencies. I'm going to do V out divided by V in, absolute value. And at low frequencies, then I'm going to not get very much. But then when I get to higher frequencies, I'm going to get 100%. So this here, this little ticker here could be considered as 100% or 1. So this is called as a high-pass filter. In other words, measuring the voltage drop across this, this resistor here. Another way that we could just simply write this is that, that you could say that my transfer function was just equal to this, whatever this complex number is here, without the v tilde. So in other words, if I wanted to, well, let's see here. So if I wanted to, for example, just simplify this here, and let me take this back over here. I'm going to take this guy over here, and if that's my I, which is just v tilde over r plus zc, then I can write delta vr is equal to I times r. So that's equals to basically v tilde over r plus zc times r. So actually, I could write my transfer function, my v out over v in. Actually, let's not even do it as an absolute value just yet. I could write that as equals to r over r minus I over omega c. So actually, for example, dividing the r's on both sides here, I could write that as 1 over 1 minus I over omega RC. So maybe just an alternative way of writing this here. Maybe it seems a little bit like mathematically less intensive. And then the only thing I need to do at this point is to just do the math that it takes to turn this into an absolute value if I wanted to figure out the amplitudes. Okay. So now, what if I wanted to measure the voltage drop across this capacitor? So I'd put some probes here on either side of the capacitor, and I'd measure delta VC. Well, at this point, it's actually a pretty straightforward math problem because we could either do this situation here where we have this I with amplitude and phase times ZC, or we can do the complex notation. So let's, doesn't really matter, we can do either one. And I'll put this in pink just so we can differentiate what we're doing here. So the current is going to be the same. So the voltage drop across the capacitor is going to be equal to I times ZC, which, as we said here, was equal to simply V tilde divided by R plus ZC. And then this is going to be multiplied by ZC. So it's almost the same thing. And we'll have here minus I over omega C divided by 1 minus I over omega C. And this will be all times V tilde. So in other words, if we wanted to do V out over V in, we're just going to be dividing both sides by V tilde. And so V out over V in is just going to be delta VC divided by V tilde. I should maybe just remind ourselves that these are all tildes here. And I can write this then as just this part here, which, let's see if we can simplify it a little bit here. I'm going to multiply top and bottom by omega c, or even minus I. Let's see, why don't I multiply top and bottom by omega c? So I'll have minus I over r omega c minus I, okay? And then I could multiply even by a minus I, or actually why don't I just multiply by an I on the top and the bottom here. And it looks like that's going to give me minus I times I is 1. And then I'm going to have minus I times I, so 1 plus I omega RC. So that's interesting. So it looks like we have a kind of a similar type of expression here. And again, this is going to be my transfer function. And so if I wanted to take V out over V in absolute value here, then again, I could just do something where I just multiply the top and bottom by the complex conjugate. Okay, so 1 minus I omega RC. And I'll get 1, let's see here, actually, you know what, actually, maybe a little bit easier way to do that instead is just simply to figure out the amplitude and phase, because really what I care about here is the amplitude. So I'm just going to say this down here is equal to the square root of 1 plus omega RC squared. And then we're going to have some e to the I phase. And of course, we can figure out the phase if we'd like to through this arctangent like we discussed. But really, this is the part we're really interested in here. So this part is going to be equal to 1 over the square root of 1 plus omega RC squared. So that's actually great. So we're actually getting somewhere with this. What if I had an omega that was really big in this case? Well, I could actually say that if omega is really big, then that term dominates over the 1, and we have V out over V in is really really So if I wanted to plot then as a function of omega, my transfer function, V out over V in, then you could actually see that for really high omegas, we're very small. What if omega was 0? Well, then I'd have 1 over 1 plus 0. Well, looks like that's just going to be 1, so 100%. So at low frequencies, we'll have 100%, and at higher frequencies, this thing will cross over. And actually, one of the things that we can say is that when omega is approximately equal to 1 over RC, that's kind of this crossover point here, both in this case and in the case over here. And exactly how that's defined is usually, I think, well, usually the way it's defined is that when omega is equal to 1 over RC, this is called kind of the cutoff frequency. And if we wanted to turn it into an actual frequency, we would have to then remember to use that frequency is equal to omega divided by 2 pi, right? So there's that kind of 2 pi factor in there that we have to be considering. But nonetheless, we'll call this as a low-pass filter because if we were to measure a voltage drop across this capacitor here, then only low frequencies would be measured, but high frequencies would be not measured very much. So finally, in summary, I will draw now what is typically called as a high-pass filter. And so the normal way of drawing this is that you have a resistive component, and then your, oops, let me draw it appropriately here. So our high-pass filter, we're going to have a capacitor and then a resistor. And usually we're talking about a voltage that we're going to hook up across this capacitor and then going through this resistor to ground. And then we're going to measure the voltage drop across the resistor here. So we have a capacitor, we have a resistor, and in this case, you can think of it as that for low frequencies, current is blocked essentially by the capacitor. And so only high frequencies are able to charge and discharge this capacitor more quickly. And so the voltage that is measured out here, compared with the voltage that's measured in, only passes the high frequency components. So this is called as our high pass filter. Whereas in comparison, we typically draw a low pass filter as when you apply a voltage in across 2 terminals, and you have the resistor, and you're measuring a voltage drop across a capacitor. And so here, if I measure V out, now if I had low frequency components, those current components are going to be able to go through, whereas if I had high frequency current components, you could imagine that they're going to short to ground across the capacitor, so we wouldn't actually have a measurement of any voltage drop across the capacitor at high frequencies. And so this is a kind of a symbolic diagram for a low-pass filter, something that shows up very common throughout all types of circuits in electronics. So I think that's about it for now. We've done a lot of great work here to understand how we can use complex impedances to make some inferences about, for example, what a voltage drop across a circuit element is going to look like. And we did that by first computing the total amount of current that's going through a circuit. And then if we had any element that we were interested in, we just needed to know how much current was going through it, and the voltage drop across any element then was equal to the current times the complex impedance for that element. So that didn't matter whether it was a resistor or an inductor or a capacitor. All those phase lags and leads were all built in to the effective Z, which really does make things a lot more convenient. And so some of the heavy lifting that we had to do was actually in essentially massaging the form. So you can imagine that after just this one step here, we were basically done, right? The rest of it was all kind of trying to massage it into the format that we wanted, getting it into this sort of amplitude and phase. In other words, taking something that's an A plus IB and converting that into an amplitude and a phase, so an A and a theta, right? So converting those things was part of most of the work that we had to do. But then what we were able to do is we could figure out the current that was going through a circuit. We could figure out the voltage drop across any of these elements. And then lastly, we could actually calculate then the frequency dependence of these kinds of voltage drops. And this turns out to be a very useful thing for a lot of circuits. So for example, imagine that you were using an AC, you were using the wall voltage, which is 115 volts RMS at 60 hertz. And so you have a 60 hertz signal, and let's say you want to get rid of that 60 hertz. Well, then in that case, we should use a low-pass filter. So simply by picking the right resistance and capacitance, you can actually choose to only for example, only let through low frequencies that might be lower than 60 hertz. So in a lot of cases also, you might find that there are signals that you don't want if you're trying to make a scientific measurement. And so you could actually sometimes combine a high pass and a low pass filter. For example, if I combine these two curves, I might have a high pass that looks something like this, and I might have a low pass that looks something like this. And if I combine the two, I might actually find that I get some curve that looks something like this as a function of frequency. And so I can filter out just the signals that I might be interested in for the particular measurement that I might be doing. So anyway, I hope this helps, and I hope that it was interesting for you to work through some of these things on the learning class. And I hope that you are able to then apply this to other circuits. So for example, what if I were to add an inductor in here? How would that change this analysis? Those are things that would be very helpful to practice and make sure that that you can master as you work through complex impedances. Thank you.